This presentation is going to discuss two new features of the Oracle 19C database that affect collection of statistics. My name is David Kurtz. I work for the TRUNCATED group and I specialize in performance tuning. Mostly I work with PeopleSoft on the Oracle database, but I also see other systems. I've written a book about PeopleSoft and I blog about Oracle and PeopleSoft. For this presentation, I've picked two new features in 19C that affect the way statistics are collected. The real-time statistics collection feature and the high-frequency automatic statistics collection. Now, at the moment, these features are only available on engineered systems and those parts of the cloud built on engineered systems. The optimizer is a piece of code inside the database. It determines how to execute your SQL statements, which table to start with, whether to use an index, and if so, which one, which method to use to join two tables or row sources together. Initially, it was an entirely rule-based operation. It performed static analysis on your SQL statements and then applied a set of fixed rules to determine an execution plan. Now that method now dates back 40 years as far as Oracle 2. It's a method that Oracle themselves still use in some of the data dictionary views, but it's not one that we're allowed to use anymore. Instead, in 1992 in Oracle 7, it was superseded by a cost-based optimizer. Now here we collect volumetric statistics about tables and their indexes, things like the number of rows, the number of blocks, the number of distinct values in each column, the range of values and distribution of values in a column. And we feed that into a mathematical model that calculates the amount of work that it is expected to have to do to execute every possible execution plan. And then it picks the plan that requires the least work, the one with the lowest cost. Now there's an implicit assumption there that the amount of work and therefore the time it takes to execute a SQL statement is going to be proportional to the cost calculated by that mathematical model. Now, there are certainly places where that assumption breaks down, where the optimizer's cost model, the calculation that it performs, is flawed, and that leads to suboptimal performance. What is certainly true is that if you don't put accurate statistics into the cost model, you really cannot expect it to produce the correct optimal plan at the other end. So quite a lot of effort, quite rightly, goes into producing the best possible statistics. And over the years, Oracle have done a lot of work on this. It's an ongoing, never-ending process. To pick out just a few, we now have the DBMS stats package. It replaced the analyze command. And it handles all the aspects of collecting and managing statistics. Histograms were introduced to describe the degree to which data was skewed. By default, out-of-date or stale statistics are maintained during an automatic overnight maintenance window. If there are no statistics on an object, Oracle will dynamically collect some on the fly during parse, and it can also do this if you have set it to check on the correlation between columns. We can now control the way statistics are collected on each table declaratively by specifying statistics preferences, effectively modifying the default behavior DBMS stats on that table. So now we spend a lot less time building our own esoteric scripts to collect statistics the way we need to. We merely specify the preferences. Cardinality feedback, now called statistics feedback from Oracle 12, lets the optimizer correct statistics based on its previous experience. If it says, well, I got a different number of rows out to what the statistics said I should get, if it repeatedly executes that statement, it will adjust the statistics. Adaptive plans in Oracle 12 allow the optimizer to change its mind about things such as the method used to join two tables. It can switch between nested loop and hash join, or vice versa. There's a new lighter weight hash-based calculation of the number of distinct values, and it produces better answers. So these are just a few points amongst many that show there's been a continuous ongoing effort to improve the effectiveness of the cost-based optimizer. And the two features I'm going to discuss in this presentation are an ongoing part of this effort. Now, both of these features are also about automating those improvements to statistics. And that's certainly part of Oracle's story, that the database is a self-managing thing. And it's a part of their autonomous proposition where it looks after itself and takes its own decisions. So I don't think we should be entirely surprised that they're Exadata-only features. Dave ENSOR was once called the grand old man of performance optimization by no less than Jonathan Lewis. I used to thoroughly enjoy going to Dave's presentations at UK AUG meetings, and I'd like to think that over the years I've learned a little bit from both him and Jonathan. Now Dave has long since retired from the software business to go motorcycling, but he is credited with this statement, known sometimes as the ENSOR paradox. The only time that it is safe to gather statistics is when to do so would make no difference. Now this is a deliberately mischievous statement and therefore entirely typical of Dave. So let's unpack what he's getting at. What happens after you've gathered statistics? Well, the execution plan might change, or it might not change. But what happens if you don't gather statistics? Well, the problem is the execution plan might still change because the data has changed. The application carries on, the data changes, the literal and bind variable values change, and they move outside the range of the column statistics or into an area of different skew, and that changes the cardinality calculation, and as a result the execution plan changes. So it begs the question, why do we gather optimizer statistics? And I think what Dave was getting at is that we do this so that the execution plans remain the same. Maintaining good, up-to-date statistics is a fundamental part of application stability. Let's talk about real-time statistics. This is what the Oracle documentation says about real-time statistics. They recognize the risk of feeding stale statistics into the optimizer. So normally, unless your application maintains statistics, the statistics on a table won't be maintained until the maintenance window after they are deemed to be stale. Table monitoring counts the number of changes, and when the number of changes are sufficient that the statistics are deemed to be stale, it will then be picked up by the maintenance window and statistics will be refreshed. Now in Oracle 12, they introduced the concept of real-time statistics for create table as select commands and for the first direct path insert into a table. And so now in 19C, they've developed that and extended it to maintain statistics on conventional path DML. And they recognize this is to plug the gap in the latency between the application changing the data and the statistics changing to reflect that. It's important to note that real-time statistics augment the statistics that are already there. So you have to continue gathering conventional statistics in the first place before you get real-time statistics. Table monitoring has been around for a long time. It was introduced in 10G and it's been enabled by default in 11G. And as I said, it's used to determine whether statistics on a table are stale. It counts the number of changes to the table in memory, and periodically SMON flushes that out to disk. By default, it's approximately every 15 minutes. But you can flush it out yourself with the flush database monitoring info command. So what happens during DML? How are these real-time statistics created? Well, if you trace it, you will not find a call to DBMS stats. In the execution plan, you will find an operation called optimizer statistics gathering, and this is the act of collecting the data. So the statistical changes are tracked along with the number of data changes, and they can also be flushed along with the monitoring data using the flush database monitoring info command. And you can then see your real-time statistics in the data dictionary, in the DBA tab statistics and DBA tab col statistics views. And there'll be additional rows, and there's a note on that row that says stats on conventional DML. And where you see that, that's real-time statistics. Over the next few slides, I'm going to show you some simple tests that will illustrate the behavior of real-time statistics. Each test builds a table, populates it, and then we'll look at the statistics and the real-time statistics and the effect they have on the execution plan of a very simple query. And I think this will reveal the behavior of real-time statistics and perhaps suggest some limitations and risks to the feature. Each test will look very similar. I'm going to build a simple table. Column A is the primary key. Its contents is uniformly distributed. I'm going to put 1,000 rows into it, and then I'm going to put 10,000 rows into it. Column A2 is a deliberately skewed column. I've used a square root function. So A2 starts in the range 1 to 32, but later it's going to be in the range 1 to 105. So we'll look at what happens with skewed data in particular. And then at the end, I'm going to flush the monitoring information so that I can see the real-time statistics. Here's the execution plan of that insert, and you can see there's an optimizer statistics gathering operation. This is where the statistics are picked up by the optimizer, ready to be written to memory. After each test, I'm going to run a simple report on each of these 4 data dictionary views to see what statistics I have on my table, both conventional statistics and real-time statistics. Now, on this occasion, I have no statistics at all, and that's because I didn't explicitly collect statistics on the table in the first place, so I didn't get real-time statistics thereafter. I still got the line in the execution plan that says real-time statistics were collected, but because there were no conventional statistics, they were never stored in the data dictionary. So, if you want real-time statistics, you must collect normal statistics first. I'm going to do the test again. This time, the first insert will be done in direct path mode, so it will collect real-time statistics, real-time conventional statistics on the table, and then I'm going to add another 10,000 rows, and we will get real-time statistics after that. So here are my statistics. Note that I have not yet flushed the monitoring information to the data dictionary. So I have statistics and I have real-time statistics on my columns, but not on the table. Let's look at the execution plan of my simple query. There's a note to tell me that real-time statistics were used. But let's look at the full table scan. It expected 425 rows, but it actually got 1,764. Why? Well, it does now know that the maximum value on A2 is 105, so it got 42/105ths of the table. But it doesn't have real-time statistics on the table. It only has the original traditional statistics, which say there were 1,000 rows. So the estimate is 425 rows. If I now flush the statistics to disk, now I have real-time statistics on my table as well as on my column. If I run the same query, I've had to add a comment to force a parse, otherwise I'd get the same statement, the same plan from library cache. Now, I still get my note to say I've got real-time statistics, and now the estimate is 4,680 rows, and the actual hasn't changed. And that's now because it knows there's 11,000 rows on the table. So, real-time column statistics really are real-time because they're immediately available to the optimizer, but real-time table statistics do not become visible until the table monitoring information has been flushed. Also note that creation of real-time statistics do not invalidate cursors in the way that normal statistics do. So, assuming you have the kind of application that requires it to parse new SQL statements, there are various opportunities for the execution plans to change as the real-time statistics become available. Let's do the test again, but this time I will explicitly collect a histogram on the skewed column A2 before I insert the second batch of rows. So you can see that I've got my real-time statistics at column level, but not at table level because I haven't yet flushed the monitoring information. And you can also see I have a frequency histogram on column A2, which shows that the high value is 32, and that there are 32 distinct values. Let's look at my query now to see how many rows have got A2 less than 42. I still have my note telling me I have real-time statistics. The estimate is 1,000 rows, and of course I actually get 1764. Why is it 1,000? Well, the optimizer is told by the histogram that the maximum value is 32, and I've got 32 buckets in my histogram. And it tells the optimizer that all of the buckets in the histogram are returned by the query. And it knows that there are 1,000 rows on the table. So now I've flushed the real-time statistics, and I have real-time statistics at table level that tells me I've got 11,000 rows on the table. I'm going to repeat my query. I still have my note that tells me I've got real-time statistics, but now the estimate is 11,000 rows, although the actual, of course, is still 1764. Well, the optimizer knows that there are 11,000 rows in the table. The histogram tells it, through the frequency histogram buckets, that the ranges of values are 1 to 32, even though the column min-max values in the real-time statistics say that the maximum value is 105. The histogram is taking precedence over the column statistics. and tells you, the optimizer, that all of the buckets are going to be returned and the number of values in the frequency histogram, which is 1,000, is scaled up to the number of rows at the table statistics, which is 11,000. 100% of the bucket, 11,000 rows, get returned as an estimate. Wrong. So what we see is that histograms take precedence over column statistics. This is actually perfectly normal. What happened here was that the proportion of rows to be returned was calculated from the histogram without reference to the min-max value on the column statistics. Now, real-time statistics is a lightweight in-memory feature. It just looks at the rows as they get updated. It doesn't do anything that requires scanning the whole table. So you don't get anything like histograms, you don't get an update to the number of distinct values. Skewed data has always been a challenge for the optimizer and in performance problems, and that doesn't change with real-time statistics. And I think you're going to find that where you have histograms, they're going to effectively render some of the aspects of real-time statistics impotent. When we're talking about histogram collection, there are a couple of other new parameters that may have a bearing. Optimizer gather stats on load hist causes the database to collect histograms as well as the ordinary table and column statistics during the direct path load. And this undocumented parameter is set on autonomous data warehouse. And there's another parameter, optimizer gather stats on load all, which makes the database collect statistics on all direct path loads into a table, not just the first one. And this is also set in autonomous data warehouse, part of the load and go approach. So you may find that you have histograms more prevalently than you might have expected. This raises the question, should we collect histograms by default? Well, the default in Oracle is to collect histograms where there is skew in usage. The global preference for method opt is for all column size auto. Oracle's advice, and you can find lots of presentations on this subject, quite often given by Maria Colgan. Oracle's advice is leave the default as for all column size auto, manage by exception, and where you don't want a histogram on a column, set a table preference that just for that column sets the bucket size to 1. But it's still for all column size auto and all the other columns. Now, on the other hand, Jonathan Lewis says don't gather histograms, not unless they're frequency or top frequency histograms, and don't use size repeat in 12C, because that could turn into a height balanced histogram. He goes further. He says change the global preference for method opt to for all column size 1. In other words, don't collect histograms at all, but manage by exception so that where you do want a histogram on a particular column, you set a table preference and you specify the bucket size. And if that doesn't work for you, you'll have to write scripts to manufacture unusual histograms. Now, I've seen Jonathan and Maria at UKOUG argue this back and forth, and it's very entertaining. And it's interesting to see what they say about the behavior of the optimizer. I'm certainly not going to adjudicate between these two points of view, other than to say an overabundance of histograms is not going to help you when it comes to using the real-time statistics feature. I think the one weakness with Jonathan's approach is that he's asking you to change a database default, and you have to then live with that and understand the consequences. Which is the right route? I can't say. It depends. Just to close this out, I'll repeat the test, but this time I'm going to gather explicit statistics at the end. Now, when I look at the statistics in the data dictionary, I get the right number of rows on my table, but I don't get any real-time statistics. It's not really surprising. If I've freshly collected statistics, they don't need to be augmented by real-time statistics because they're right. So when you collect statistics, it deletes any real-time statistics. And when I look at the execution plan, now the estimate is spot on. It's really close to the actual number of rows. So what's happening here is that the up-to-date histogram produces an accurate estimate on the skewed data. There's a few little quirks I've come across while I've been investigating the feature. So here, I'm going to delete some rows from the table and I'm going to flush the monitoring information to disk. I don't get any real-time statistics. So the delete does not appear to be tracked. Here, I'm updating the table. A2 is going to be updated. The range changes from 1 to 32 to 22 to 39, and I've prefixed column B, and I'm updating half of the rows. Flush the monitoring information, and let's look at the statistics. So I got real-time statistics. The number of rows hasn't changed, but the blocks has gone up from 5 to 7. It's picked up the increase in the maximum value on A2 from 32 to 37, but the minimum value remains 1. It cannot increase the minimum value or decrease the maximum value because that would require scanning the entire table, but it can increase the maximum value and decrease the minimum value. Note also that I've only got real-time column statistics on A2 and B and not A because I didn't update A. I found that if I update and then delete from the table, I do get column statistics. So here it has correctly detected that the number of rows is decreased from 1,000 to 800. And again, I've got column statistics on A2 and B, but not A. When I query the table and look at the execution plan, it says it's used real-time statistics. It estimated 160 rows from the table, but it got none. So it still thinks that the range of values on A is 1 to 1,000. So greater than 800 is about a fifth of the range, 200 rows. But it thinks that there are only 800 rows now. So it's 800 times a fifth is 160. Truncate has never removed statistics. So here I'm going to populate the table, truncate it, and then add a bit more. And when I look at the real-time statistics, it's quite rightly said, well, there's now 10,000 rows on the table. That's perfectly correct. You can see that the maximum value is close to 11,000 on A. So when I query rows less than 501, the plan says that I did have real-time statistics, and the index range scan expected 459 rows, but it got none. It got none because we truncated the data in the range 1 to 1,000. But the statistics suggest that A is in the range 1 to 11,000, and so it estimated about 450 rows. It got it wrong. Once again, the column statistics have misled it. It's surely a bug that the deletes are not tracked by real-time statistics, because updates are tracked and deletes after updates are tracked. Truncate has never deleted statistics, either conventional statistics or real-time statistics, so that's not surprising in itself. But it is clear that you can get statistics based upon truncated data, then mixed with real-time statistics based on the new data, and that can cause confusion. In this test, we're going to look at what happens as predicates move outside the column range of statistics, and I'm going to look at uniform distribution. So in the first test, I'm going to insert rows with n 1 to 1,000, and I'm going to look at the number of rows greater than 900. Then I'm going to add another 1,000 rows in the range of 1,001 to 2,000 and look at rows greater than 1,900. And finally, I'll collect real statistics and show you what happens there. So here's the first query with just statistics on load. It estimated 101 rows greater than or equal to 900, and it got 101 rows greater than or equal to 900. So that's absolutely right. So now I've done the second insert and I flushed the monitoring information to disk. You can see that I've got my conventional statistics with 1,000 rows and my real-time statistics that say I do now have 2,000 rows in the table. Quite right. It's picked up that the maximum column value of A has changed. It thinks it's 1984 because it hasn't captured every row that's come past, but of course it's actually 2,000. Here's the execution plan with the real-time statistics. It's estimated that it's going to get 87 rows, whereas it actually got 101. So the estimate is slightly off, and it's off because the maximum column value was recorded as 1984, not 2000. So that's how it comes out with 87. So it's a pretty good estimate on a column without skew. And this is the problem that real-time statistics was designed to solve, and it actually solves quite well. However, note that here we got a full table scan. This is the execution plan having refreshed the statistics. The estimate is 101 rows, and we get 101 rows, so it's spot on. But notice, we now use an index range scan. So the more accurate statistics produce a more accurate estimate, but they produced a different execution plan. This time, I'm going to create a global temporary table. I'm going to use onCommit preserve rows. I don't get real-time statistics on a global temporary table. I get the normal shared statistics, and I've enabled session private statistics that correctly note that I have 1,000 rows in the table. Now, the concept of real-time statistics just doesn't fit with global temp tables. Statistics on global temp tables have all been problematic. They're global because the content is private, and they're temporary because the definition is permanent. Or if you prefer, they're global because the definition of the table is available to all sessions, but they're temporary because the physical instantiation of the table is temporary and private to the session that created it. Each session has its own physical copy of a global temporary table. When you collect statistics on a global temp table, the problem is you may collect it in one session, but they may get picked up and used in another session, and those two sessions may have totally different data in the table. So Oracle introduced the concept of session private statistics on global temp tables. They're stored in memory and exposed via an $X table. But global temp tables are designed for short-lived temporary working storage of data. If you're going to use real-time statistics, you're left with all sorts of questions. First of all, you have to wait for the monitoring information to flush to disk. Is the session even still going to be there with its global temporary table? And then, which session statistics will be stored and flushed? And where are they going to be flushed to? And you'd have to have had conventional statistics collected also. The concept just doesn't fit, so it just doesn't happen. If you lock statistics on a global temporary table, and I'm going to lock the statistics here after the initial insert, but before the subsequent conventional path update, then you don't get real-time statistics. You get the normal statistics on load. If I'd locked the statistics before the first insert, I'd have had no statistics here at all. Locking statistics on a table prevents collection of those statistics during a schema or database-wide operation, for instance, during the maintenance window. Locking statistics also prevents collection of real-time statistics, either during the initial direct path load or a subsequent conventional path load. The usual reasons for locking statistics are either because we don't want explicit statistics at all, perhaps because we're going to rely on dynamic sampling, in which case there's nothing for real-time statistics to augment, or because we're going to manage the statistics manually ourselves on our own timescale, or perhaps during the application. And if that's the case, there's no point confusing the issue with real-time statistics. Despite the problems I've outlined, I think real-time statistics are going to be a useful enhancement. However, if you want, you can disable them. There are two undocumented parameters that can be set at either system, session, or statement level. One parameter controls whether you gather the stats. The other parameter controls whether you use the stats that you have gathered. They both default to true, but you can choose to set them to false. There are also two documented hints. No gather optimizer statistics will prevent real-time statistics being updated in a particular statement. Gather optimizer statistics simply reinforces the default behavior, but it doesn't override the underscore parameter if you've set that to false. What does not exist is a table preference for real-time statistics. So it's not possible to say, I want real-time statistics on this table, and I will decorate it with a preference, and I don't want it on that table, and I'll decorate it with a different preference. The no-gather optimizer statistics hint has two functions. It was originally introduced in Oracle 12.1, where it can be used to suppress the collection in real time of normal statistics during the initial direct path load into a new table. In 19, it can be additionally used to suppress the collection of real-time statistics during the subsequent conventional DMLs. So here's an example of the hint used during the initial direct path load. I don't get any statistics at all. I don't get normal statistics, and therefore I don't get real-time statistics. And here is the hint used only in the second conventional path insert, and now I get normal statistics on load, but I don't get real-time statistics. So in general, real-time statistics are going to give you more accurate statistics that are going to result in fewer problems at least, if not better performance. Skewed data has always been a challenge, and it's still going to be a challenge with real-time statistics. It's really clear there is no substitute for maintaining the right statistics in the right way at the right time, even if that means collecting statistics during application execution. I'm going to turn my attention now to the second feature, high-frequency automatic optimizer statistics collection. Quite a mouthful, but that's what Oracle call it. It's a new procedure in the DBMS stats package. It's very similar to the automatic statistics collection job that runs in the maintenance window that we've been used to since Oracle 10. However, it's not enabled by default. You have to decide to turn it on. And when you do, it applies to the whole database. You have no discretion in that. The key difference is that it has a limited runtime so that it can be run more frequently. only one instance will run concurrently, so it should normally only consume one CPU, although of course you can end up collecting statistics in parallel. The batch job will run during the maintenance window. The process is driven by this sys_stats target dollar table. It works from what it considers to be the stalest table first. And I believe this table is also used by the maintenance window job, and it's used to prevent the two jobs from running concurrently on the same table. This process is going to interact with real-time statistics. The DML activity that will generate real-time statistics may also cause the table to be considered to be stale, and if it's stale, it's going to be picked up by high-frequency automatic statistics collection. So you may find that real-time statistics appear and then disappear when this job runs. I think this job has some consequences and some potential threats. The first thing is cursor invalidation. When you update statistics, you're going to invalidate cursors. So you may find that your cursors disappear quite quickly after a process completes as the statistics collection occurs. And this might lead to increased parse overhead. It's also going to have an implication for statistics history. Every time you collect statistics, the old statistics are saved to the history. So you're going to get an increased volume of statistics history retained, and you may have an increased overhead for the processes that purge from the statistics history. You've got very limited control of this job. You can either turn it on or turn it off. You can specify the execution frequency. The default is every 15 minutes, 900 seconds. And you can set a maximum runtime, and the default is 1 hour. And of course, if you lock statistics, it's also omitted from this job. You can read the current preferences by reading the preference, and these are the default values. You can track how the job is behaving by inspecting DBA autostat executions, and you can write a little report that tells you how it's getting on. You can see the number of tables that it processed and how long it took to do that processing. It always seems to report one failed table. I haven't been able to work out what that table is. The stats target dollar table is used by the high frequency stats collection process to control what happens to each table, and it also logs what happens. So you get timestamps and when stats collection begins and ends. You get this staleness value, which is a number in the range plus minus 100, and it's a mathematical estimate of how stale the statistics are on a particular table, and it's used to control the order in which statistics are collected. The process starts from what it thinks is the stalest statistics. You get some information about the object number, the type, there's a status flag, and some information about the partitioning. You can write a report on this table, join it to the sys_obj$ table, and then you can see which tables and partitions had statistics collected on them and by which process and when. So, in conclusion, both of the features I've talked about today are Exadata features. I think they're primarily aimed at the autonomous transaction processing databases, not so much the data warehouse, because you tend to do direct path load and then not update the hybrid columnar compressed objects. And it will apply, therefore, to other forms of Exadata. I think it will be very interesting to see a classical ERP on Exadata on 19C and see how it behaves. I think it's a shame it's not available on non-engineered platforms. I think it would help them also. But I think that is a political decision rather than a technical decision. If you set this underscore exadata feature on parameter, you can reproduce all of the behavior I've described today on a non-engineered database. Now, obviously, we'd never do that in the real world, but it does show that the feature is there and it could be made available. Real-time statistics are there to avoid plan regressions caused by using stale statistical data. Clearly, they're going to work well with uniform distributed data. They augment the statistics that are already there with simple metrics, row counts, min-max values. But they aren't going to collect anything that requires a scan of all the data. So no histograms, no numbers of distinct values. And we've seen they get tripped up by skewed data. The mechanism is based on table monitoring. It does not call DBMS stats behind the scenes. High-frequency automatic statistics is part of DBMS stats. Think of it as a continuous maintenance window that recollects statistics that are stale, starting with what it thinks are the most stale statistics within each object type. I do worry, though, it could repeatedly get stuck on a large but stale table in ways that I've seen the overnight maintenance window also get stuck. These are the kind of tables that you need to take out of the maintenance jobs into your own job. So, we've reached the end. Thank you for watching. Please feel free to ask questions either by email or by leaving comments on the blog or recording. Thank you.